listening to The Switch. The Switch is a podcast about ideas and experiences that change our minds. I'm Chase Harris, joined as always by my co-host, Alex Berner. In this episode, we speak with John Azariah. John is a principal software engineer at Microsoft Research Redmond and a member of Microsoft Quantum Redmond. He's currently the lead of Q#, the new programming language for quantum computing. He talks a little bit about his bio in the interview, but John's focus is software languages and functional programming.
If you like what we do here on The Switch, the best way to support us is through Patreon. For as little as $1, you can become part of the community. Ask us questions, suggest topics, and directly communicate with us. You can also unlock bonus content, like extra questions we ask our guests. If you want more of The Switch, both on topic and off, you can become a patron at www.patreon.com/switch_podcast. You can also check us out on social media. On Instagram and Twitter, we are at switch_podcast, and on Facebook, we are The Switch Podcast. The Switch is produced by Mojo Filter Media, a company specializing in audio production for video games and interactive media. You can check out our website at www.mojofilter.media.
Cool. So, Alex, you wanted to clear up some things or make some clarifications before we really get into this conversation.
Yeah, so I'm not very familiar with the intricacies of how computers work, and this topic is not the way quantum computers work, and quantum physics isn't even totally understood by those who work in the field.
Right. The common conception is that, the math is really robust. We know the math. The physics is mostly robust, and we pretty much get it. But a lot of the behaviors, as far as I know, are things where we know what it does, but we don't really know why.
Yeah, these are properties that happen in nature that we can't quite understand why it's happening, but yet we're learning how to use them.
There's basically no doubt at all that these things exist the way that they do. It really is the question of why.
Yeah, and so there's a lot of counterintuitive properties in quantum physics that we actually are probably going to go into in another episode, because it's really interesting. I think you used the word spooky.
Mm-hmm.
It almost seems magical, but my perception of it is it's basically these truths and ways that nature works that we really don't understand.
Yeah.
And we might just not be able to perceive them based on, our senses, how powerful our brain is, but they're there and we're learning about them.
I will link in the show notes a video talking about this property called wave-particle duality. And it's specifically talking about light and how photons act as both particles, individual little packets, and waves, energy that propagates through a medium. And if you're really interested in trying to understand how spooky some of these properties are, I would encourage you to pause the podcast, go watch the video, and sort of watch your reaction to it, but also just understand that this is the way that quantum mechanics is understood. There are a lot of things where we can very robustly reproduce the results, but the answer remains, like you said, spooky.
Yeah.
And that video, I think, is only about 10 minutes long, 8 minutes long, something like that. It's very interesting, but
yeah, I second that, because it's something that is more easily shown with visuals and approach from different ways to try to help our brains understand something that doesn't make sense.
Yeah.
So if you're new to quantum physics, or just don't even know the word quantum or physics,
hopefully you know the word physics, but
yeah,
you can be forgiven if you don't.
Yeah. I would highly advise you to check that out. If you're interested in it, maybe look a little bit more into it. But there's still stuff in this podcast that you can take out of this without fully comprehending that.
Yeah, absolutely. And actually, that's one of the reasons, and I explained this a little to John in the beginning. One of the reasons that we're talking to him instead of a quantum physicist is because I really wanted to drill in on the implications of things. I really wanted to talk about where is the technology leading? What can it allow us to do? Rather than getting bogged down in the spookiness of the physics or, what the experiments look like, because that's not really the real world application. And, this is a guy whose job is the real world application.
And another thing I wanted to cover before we start the podcast is the idea of computer language.
Sure.
So this is something that is basically runs parallel to our language for our world.
Yeah.
There's all these little things that happen in our everyday lives, and for us to be able to understand them and talk about them, and write about them, or anything that's useful, we need to categorize things and group them. So if you think about running, we all understand what running is. But if you break it down, it's taking a step and another step in a certain speed, in a certain direction. And it can be broken down into all of these different actions or things that are happening. But it's not really useful to talk about it in that way. And it could be the same with an object, a person. We are, made up of organs and skin and molecules and atoms, but we can't talk about that every time we mention a human. We just need to use the word human, and then we got what makes that up.
So computer languages run across the same lines. They're analogous to human languages, like you were saying. In a computer language, at the sort of highest top level, you have certain commands or functions or ideas that you want to get across. So let's say you've got two variables and you want to do some transformation on them. A computer language will basically let you manipulate data in a way where you can think very abstractly about solving your problem, and you don't have to worry about things like managing memory or figuring out where to store some piece of data. The computer will figure that out for you. It's also a way of abstractly putting together combinations of functions. So for instance, if you want to do prime factorization, you can actually just put in a command for prime factorization, and the computer has stored all the steps required to factor a number into its prime factors. And that it's like that all the way down. So you could even talk about something as simple as addition, where you have one number and another number, and you want to add them together. That's a series, at its most basic level, that's a series of binary operations that's operating on zeros and ones that represent the number, and zeros and ones that represent a set of instructions for certain operations to perform on the other sets of zeros and ones. And it would be way too complex to every single time you wanted to add two numbers together to remember which combination of zeros and ones to put where. It's way easier to just have a system, almost like a dictionary, where you use this command and the computer interprets it.
Mm-hmm. Yeah, and if you thought about expanding that out even further, you'd get something like maybe double clicking on an icon. If you want to go even further out, then telling it a word in the computer language, we make it more and more basic for users and programmers to efficiently interact with computer software in a way that is useful. So I just wanted to get that out of the way so you understand kind of what John's goal is with creating a new computer language. He goes into it towards the end. But there were also a few other terms just before we start that I want to define And Chase, if you could just define a transistor.
Sure. So a transistor, when we're using computers, the theoretical sort of abstract idea of what we're working with is something called a bit. And that's something that can be in one of two states. Usually that's represented as a 0 or a 1, or off or on. Now, you can represent that any way you want. You could use a coin, right? Let's say heads up is 0 and tails up is 1. Now you've just created a bit. And the physical manifestation of that bit is your coin, and you can manipulate that however you want. A transistor is an electrical component that represents a bit using electrons. That's all it is.
So it's basically, whenever we talk about bits, it's a 1 or a 0.
Mm-hmm. And in the physical world, that's usually a transistor.
And another one I wanted to ask was classical computing.
So classical computing is the term given to the types of computers that you use every single day. Your iPhone is a classical computer. The computers that we're using to record this podcast are classical. The computers that control airplanes and gas stations and self-driving cars, all of those computers are classical computers. And all that means is that they use bits. They're fundamentally made up of a series of these ideas of zeros and ones.
Mm. What's a vector?
A vector, the sort of geometric definition of it is basically a vector has direction and magnitude. So the classical geometric representation of a vector, if you just imagine a graph, and you start at the middle of the graph at point 0, 0, the coordinate 0, 0, and you put some other point on the graph, a vector, if you're calling that a vector, that's the direction and distance from the origin to the new point.
So with all that out of the way, if you have any questions or you want to learn more about this or get lost, episode's always here. And there's always Google search. Or what's Microsoft's?
Bing.
Bing. There's always Bing.
Bing hands you free money. I don't know why people don't use it. So, without further delay, we start with a quote from Niels Bohr. If you're not astonished by quantum mechanics, then you have not understood it. And with that, I'd like to introduce our guest for today's podcast, John Azariah. John, welcome to The Switch.
Hey, thank you for having me. I am very astonished.
Awesome. Well, thanks for coming. So before we get into the major portion of today's topic, which will be quantum computing, I want to get a sense of where you come from, where your background in all this, and who you are. So, John, start us at the beginning. Who are you? Where'd you come from?
Sure. Basically, I'm a computer scientist. I studied computer science and chemistry at Dartmouth way back when. I originally come from India. I have an interest in functional programming and an interest in language design. And functional programmers tend to write little domain-specific languages when they want to solve problems. So coming up with having a sense of language design and semantics and stuff like that is kind of a very useful sort of background to have. And I got that kind of bug early on in my academic career, and I kind of just stuck with it as a side gig. I used to do a bunch of stuff on the side. Professionally, I joined Microsoft way back when, and then quit, ran my own company for a while, moved between countries, several countries, and eventually landed up in Australia, where I landed up being a cloud architect for a large company in Australia, and then got sucked back into the mothership. So I came back to Microsoft a couple of years ago, And because of my interest in F sharp and functional programming and the language design and code generation skills that I'd had to pick up along the way, I ended up coming to work on the quantum computing team to build the new quantum programming language. That's kind of how, in a very short way, how I landed up where I am.
And I'm curious, what was your first encounter with the idea of a quantum computer? Do you remember the first time you had ever sort of heard that phrase or understood what that actually meant?
Oh, I don't think I fully understand what it actually means even now. I'm probably for the longest time, the standing joke was I'm probably the only language designer of any language that is actually not qualified to program in the language that I designed it. But that shouldn't put you off, because the language should actually be the entryway to make quantum computing accessible.
Yeah.
I didn't know anything about quantum computing until I joined the quantum computing team about a year and a half ago. But I do have a background in chemistry, so I'd studied quantum chemistry way back when as part of my degree. So some of the maths and the physics and the concepts behind what quantum mechanics was, that you kind of picked up that, in the early 90s as a student kind of thing.
Yeah. And actually, that's part of the reason that I'm excited to talk to you is, with this idea of quantum computing and quantum mechanics, it's pretty easy to get caught up in, just being in awe at how spooky the physics are. But, I think your expertise, at least to me, seems to be really practical and really in the side of things that's going to be taking the most leaps and bounds in terms of new technology. People are going to be doing new types of programming with this and new applications, and your expertise to me seems like you're qualified to talk about that aspect of things. But we'll sort of get into what kinds of things that you're working on. And
sure, you're very kind. Thank you very much for that.
Before we really get into quantum computing, I want to make a quick stop at the idea of computing in general. And could you sort of give a brief explanation of how a classical computer works, and then we can move on to talk a little bit about quantum?
Right. Okay. So, look, the general introduction people have towards classical computing varies. Okay. Most people understand computers as devices that basically take instructions and do things. And that if you've taken your general computer science 101, that's more often than not the introduction people get towards what a computer is. So you're likely to learn things like, way at the bottom there's a processor. You have some machine code or some assembly language that you write some code in, and then there's some memory, and you issue an instruction, and it operates on the memory, and it does a bunch of stuff. And that's one way of looking at a computer. Actually, it's only one way of looking at it. That's the key point that I want to make. Another way of looking at it is actually how they looked at computers way back in the 20s, before any of the chips were actually made. And they looked at computing as an extension of mathematics, as a way of abstractly constructing, a mathematical foundation for what it means to computation. And if you've got a little bit of background from functional programming, from the functional programming perspective, where if you think of things as values and functions operating on values and that kind of thing, that's actually a much better place to start off to understand quantum computing in general and computing itself. Because if you think about what an interpreter does, is that it actually lifts the programming abstraction of the computer to the problem domain that you want to express the problem in. whereas a compiler sort of lowers the program that you write into the abstraction level of the chip or the physical hardware. In our case, what we have to do is realize that we like to talk about things in the abstract because the hardware isn't familiar at all.
Yeah.
In fact, the whole point of quantum computing is that the hardware is exotic, behaves very differently from what we've become used to as computation. And if you go with the initial approach of, a computer must have, A, memory, B, instructions, C, some kind of thing that executes, you don't really get the sense of how to think about the problem in a nice, clean way. If you lift the problem a little bit higher, or what you're really trying to do is solve a problem, a functional problem, and you have different mechanisms for solving the functional problem depending on whether you're using a classical machine or a quantum machine. And so the abstract way of thinking about a problem has a great deal of influence about how you approach or how approachable quantum computing is to you.
Yeah, so that was actually one of the things I wanted to touch on was this idea of abstraction. And the building blocks of classical computation are bits, right? You can sort of think of them as almost like a light switch. It's either on or it's off, a 0 or a 1. And to a lot of people, you can talk about bits, you can talk about gates and logic gates and or and whatnot, but to abstract that out into useful computational packages is a line I think a lot of people don't necessarily, or connection I think people don't necessarily always make. And so, yeah, I'm glad you touched on this idea of abstraction, that we use these higher level sort of building blocks that have been put together from the smaller level building blocks to actually program. And that same hierarchy of pieces translates over into the quantum world as well.
Yes, that's absolutely right. In fact, the abstraction that is most useful to think about, if you're a C or a C++ programmer, you think about the abstraction as being, there's memory and a processor, and your instructions are effectively translated down to bit instructions that get executed down there, right? A more useful way of thinking about it, at least from a conceptual point of view, is to think about it in terms of values and functions. And once you do that, you get into this wonderful world of abstract mathematics that talks about how functions are effectively things that transform values, and you can have functions themselves be values that can be transformed. And if you go a little higher, there are other constructs, mathematical constructs, that allow you to do composition and stuff like that, where you can actually model the handling of side effects like mutation of state and so on as effectively functional constructs. Now, those things turned out to be very useful for us when we built the language, because we went very quickly from talking about operating on qubit state with certain types of fundamental instructions, if you want to call it that, to effectively talking about sequences of computations that needed to be composed together, and that sort of led naturally towards the building of a language. So there are scary words that you might find people use in the functional programming world, like monad and stuff like that. But it turns out to be quite useful to think about those levels of abstractions from a quantum computation perspective as well, because it turns out that everything that you do in the quantum world is effectively manipulating state on an exotic computation device somewhere, and that can be composed in a nice way using that model of thinking about it.
So you mentioned a term that I want to get into sort of defining, which is qubit. But before that, can you talk at all about like the nature of sort of this word quantum? Like we're sort of throwing around the word quantum versus classical. What is that distinction?
Oh, that's a brilliant question. Well, okay, so we can answer this question at multiple levels, right? The first thing to realize is that there's nothing sort of mysterious about it. Um, there's a bunch of stuff we know, and there's a bunch of stuff that we're still learning about quantum mechanics. But it is really the foundation of how nature works. And so if you look at the behavior of things in the small, if you look at electrons, or you look at things even smaller than electrons, then you'll end up finding out that the way they behave is very different from the way a baseball behaves or the way a planet behaves, right? And it's not, how do you say, it's just a consequence of the properties of matter changing their emphasis as you go from the bulk to the small. So as you move smaller and smaller, different aspects of physical properties become prominent than do the properties when you go larger and larger.
Yeah.
So for example, as you become larger and larger, the effect of mass and its effect on things like the gravitational force, they start becoming more predominant. As you go smaller and smaller, there are quantum mechanical effects like what happens when you want to look at the combination of, say, position and momentum. That stuff can be sort of calculated within experimental error in the bulk, but you can't actually do it to arbitrary precision in the small. And so the behavior changes as you become smaller and smaller. And we can sort of, nature behaves like this all the time. And in fact, nature does the equivalent of very, very complex calculations using this mechanism. And using this sort of these phenomena is really what quantum computing is all about. So if you want to think about quantum mechanics as such, it's really how matter behaves, when you look at it, in really, really small quantities or really, really at a very small scale. And they don't behave intuitively at all. They behave perfectly predictably, but it's not intuitive from that point of view.
And I think that's a beautiful explanation. That actually leads me into the main reason that I feel like this topic is, the theme of our podcast is ideas that change our minds or perspectives on things. And that, what you just explained about how, this is sort of nature's way of doing the equivalent of calculation, and the fact that things that are very, very small behave counterintuitively, to me, that was a total philosophical switch in my perspective about how the world works. And I think a lot of people, especially in the age where people are now growing up with computers and smartphones and tablets and things, many people conceptualize the world as working in this very discrete way, where we have, computers have zeros and ones, bits, but even things in the material world are either moving or they're not. They have a discrete velocity or they don't. They have, I'm over here or I'm not. The light is on or it's off. And there are these discrete sort of values of things, and they use that to abstract upward into the way that everything works. But for me, it was sort of revelatory to realize that that's not how things are, and that nature is much more analog than that. And we'll get into, it can be much more spooky than that sometimes.
Yes. And ironically, the whole idea of quantum mechanics is that the discreteness of things actually extends all the way down, so that things that look like they're analog are actually not. The whole point, like for example, when you mentioned, well, there's light or not.
Right.
That's, yeah, I guess philosophically you can understand it. But if you look at it from even from a photographer's point of view, there's intensities of light that go all the way from complete darkness to like complete white, right?
Yeah.
But if you look down all the way down to how light actually works in very small discrete pieces called photons. And then you have to have the question of, is the photon there or not, and can we detect a single photon? And then the answer is yes, we can. But the idea is that the discreteness of the thing is really what we depend on in terms of quantum mechanics. So, for example, when you mentioned the word qubit,
Yep, that's where I was going next.
This is actually, this is a beautiful segue to that. A bit is either 0 or 1. A qubit can be literally any value that is a linear combination of 0 and 1. And that turns out to be kind of a very interesting prospect. I kind of oversimplified that when I said that it could be any value. There are certain, again, criteria that need to be followed in order for it to be a proper value for a qubit, right? But if you look at, say, for example, energy of an electron, right? And this is probably something that is easier for someone with even a basic science background to be able to sort of visualize. If you think about electrons, they can't have any energy you feel like. It turns out that they have to have energies that are effectively quantized. And you have these things called electron shells, which you must have heard of way back when, where an electron in a particular shell has a fixed amount of energy. And if you give it more energy than that, it doesn't do anything until you give it enough energy for it to move from one shell to the next.
Yeah.
Right? And so you can take a physical system that looks like that and treat one of those energy levels as 0 and the other one as 1, for example, and then you will have a two-level system that you can effectively work with. And an electron at that point becomes something that you can use as a qubit in the context of having a two-level system, that the electron can be either in the lower ground state or the upper excited state. And usually when the electron falls from the upper state to the lower state, it gives out a precise amount of light. And in fact, that light, we can actually tell how much energy that is contained in that photon. Very, very straightforward way of thinking about it. Now, that physical phenomena that I just described has been well studied, and sort of we understand it from like the early 40s or whatever. But to use that as a computational device, that idea is actually almost just 10 years younger than that. So early in the 1950s or so, there was this idea that you could literally use these quantum mechanical phenomena to effectively do computation. Obviously, we didn't even have the classical computers to be able to simulate the behavior, much less have a quantum computer to actually affect the computation, right? But the idea that there's a potential for a computational device from this two-level system is actually almost as old as the discovery of the two-level system in the first place. So it's not an entirely new idea, is really what I'm trying to point out.
Okay, so I just want to make sure that we're caught up on this idea of a qubit. Could you maybe give a brief definition of qubit?
Right. So a digital bit is a discrete value that stores a single one of two states. Right.
Yeah.
If we use a transistor as a bit, well, either it's conducting electricity or it isn't. If you use a capacitor as a bit, either it's charged or it's not. Right? If you used a magnet as a bit, either it's aligned with the North Pole or it's not, right?
Yeah.
And you can basically use any of those systems to effectively store and represent a binary value, right?
Yeah.
But another way of thinking about it is that instead of treating the number as just a plain old 0 or 1, which is what we typically do when we want to do digital computation, I could quite easily turn the state of a bit into a single vector that has, a 0, 1 or a 1, 0, depending on whether it's 0 or 1. So now I have a vector of dimension 2 that can literally store either it's going to be representing a 0 state or a 1 state. And so let's see if you can imagine a beach ball. And if I imagine the beach ball with the North Pole as being the 0 state and the South Pole as being the 1 state, then a bit is either a dot being at the North Pole or the South Pole. That's easy to visualize, isn't it?
Yeah.
Okay. Now let's say the operations on the bit are effectively very simple, right? You can either flip the ball over so that the 1 goes to 0 and the 0 goes to 1, or you could leave it the way it is. And now you can effectively perform operations on a beach ball by simply rotating it around one axis so that it takes a state from being in the 0 state to the 1 state, or the 1 state to the 0 state, for example. Rotating the beach ball halfway doesn't make sense because it doesn't actually store a value. It doesn't represent a value that can be represented either as the North Pole or the South Pole. So this is in effect like a coin. It's either heads or tails.
Right.
It's either the North Pole or the South Pole in terms of the beach ball, right?
Yeah.
Now, a quantum bit is effectively the surface of that beach ball. So any point on that surface can actually represent the valid state of a qubit, a quantum bit. So not just the 0 and the 1, but any other point on the surface of that sphere as well. Now that turns out to be kind of useful because because I sneakily introduced this vector of dimension 2, right? So in the vector of dimension 2, the only things that you could have in the vector of dimension 2 are 0 and 1, and based on whether it's 0, 1 or 1, 0, you're encoding whether it's the North Pole or the South Pole, right? But now if I actually introduce 2 values instead of 0 or 1 and put those 2 values in the state vector, then I can apply the same kind of mathematics that I would in order to do the rotation from 0 to 1 and so on. I could do the same thing and more on any point on that sphere now. Does it make sense?
Yeah, I mean, it's definitely a lot to wrap your head around. And I want to make sure that we bring enough of our listeners along with us.
Sure.
There's a term that is used to talk about this called superposition.
Yes.
Is that the term for this specific phenomenon?
Indeed. In fact, this is exactly what superposition means.
Yeah.
When you take a point that's on the North Pole and move it to where the equator used to be, you're now representing something that could be partially 0 and partially 1 at the same time. The beauty of the really beauty and the spookiness of quantum mechanics, though, is that it doesn't allow you to actually ask, the beach ball won't let you ask it, where is the dot? And the only thing that the beach ball can tell you is it at the North Pole or is it at the South Pole?
Right.
So even though you have this infinite variety of states that could be held in a qubit, the qubit itself can only tell you, hey, is this probabilistically going to collapse to a 0 state or is it going to collapse to a 1 state? And whether it collapses to 0 or 1 depends on probabilistically how far down the path to the equator you've rotated the point. Right? So if you take the point from the North Pole and put it on the equator, then 50% of the time it will collapse to the North Pole and 50% of the time it'll collapse to the south pole. And that says that the qubit is an equal superposition between the north and south. But you could rotate it any amount of time, right? You could rotate it like 45 degrees instead of 90 degrees.
Right.
And then it's going to be probabilistically more likely to collapse to zero than it is to one.
Mm-hmm.
And just by using rotations now, you can actually effectively move the sphere in such a way that the dot moves all the way around to where you want it to go. And that, in a sense, is the whole idea of computing with the qubit.
Mm-hmm.
Is that you can take a zero state and then move it to wherever you need to go by applying a fixed set of rotations in that sense.
So yeah, and this is where we had talked before about abstractions, and when you're working with programming, you're using abstractions that are sort of packaged ways of talking about certain transformations on bits. In the case of qubits, you're actually talking about performing certain reconfigurations or certain transformations on these bits, sort of rotations if we're talking about the beach ball.
Right.
Is that right?
That's right. In fact, what I was trying to tell you earlier was you can model all of digital computation using the same beach ball example and with a single rotation that takes things from north to south. In fact, that's the only rotation that is allowed in a digital sense, in a classical sense.
Mm-hmm.
Whereas from a quantum sense, you can now perform partial rotations to any point on the sphere, actually. And you can use that mechanism to actually do more powerful computing.
So there are a couple more quantum mechanics terms that I want to get, but because you said you can do more powerful computing, how powerful does it get?
Sure. So bear in mind now that the kind of problems that you can solve more efficiently with a quantum computer is limited to the set of problems that you can take advantage of the fact that you can now be on any point on the beach ball, for example.
Right.
So if your problem is simply, hey, am I on or off? I don't get any benefit from the point that I can put. I don't get any benefit from the feature that I can actually move the point halfway.
Mm-hmm.
Right. So there are only certain types of problems that take advantage of the quantumness of a system in order to get a speed up. Okay. And how much speed up you get depends on the kind of system. So there are certain types of algorithms, certain types of problems that actually offer a logarithmic speed up. Okay, so instead of taking order n type set of operations to get a result, you can now get that in logarithmic time. Some of them will only give you a quadratic speed up. So instead of taking order n time, it will give you a result only in root n time. And some actually don't give you any speed up at all. So there are entire swathes of algorithms that have no benefit to running on a quantum computer.
Mm-hmm.
And in many cases, there are algorithms that will be much more efficiently run classically, just because of the availability of the hardware and the tooling and all of the other stuff that we have already. That you'd be better served using classical mechanics for doing certain types of problems. But there are certain types of problems where you get this sort of exponential speed up,
right,
which is pretty powerful from that point of view.
There was I watched one of your lectures, and one of the statistics that was given was by the time you are calculating with 260 qubits, the types of calculations that you'll do, 260 qubits, to simulate that classically would require more bits than there are atoms in the known universe. Is that an exaggeration?
No, it's not actually. It's
okay.
just So it's a slightly sensationalized way of putting together a very important point. You remember when I told you about the state of a qubit being a vector of size 2?
Mm-hmm.
Mm-hmm.
Well, it turns out that every qubit that you add to a system doubles the size of that vector. So a 2-qubit system requires 4 complex numbers to actually represent its state, right?
Mm-hmm.
And a 3-qubit system requires 8, and a 4-qubit system requires 16. Now, if you keep going up that chain, a 10-qubit system is going to require 1,000 complex numbers, and every time you add 10 qubits, you multiply the number of complex numbers that you need by 1,000, right?
Right.
So at about 30 qubits or so, you need about 16 terabytes of memory, 16 gigabytes of memory to do something useful, to just hold the state of a 30 qubit system.
Mm.
Now, it turns out that there are about 10 to the 80, or about 2 to the 240, to the 250 or so atoms in the known universe. So, if you think about how many qubits it would take to sort of occupy that space, well, that number turns out to be about 250 or so. Now, it turns out that to represent the state of a 250 qubit system is going to require a very, very large number, like I told you, the large number of complex numbers. But from a quantum mechanical perspective, you only need 250 qubits to do that. And it turns out that for some of the difficult problems that we want to solve, to be able to use quantum mechanics to solve, we talk in terms of, thousands of bits. So all that it simply goes to say is that once you reach a large number of qubits, about 50 or so, it becomes classically infeasible to simulate the response.
Mm-hmm.
And that's the takeaway from that, right? So we can classically simulate 2 to the state of 50 qubit system if we had 2 to the 50 complex numbers. That turns out to be about 16 petabytes. Which is a little more than my laptop has.
Yeah, a little.
Right. Few orders of magnitude.
Yeah.
Right. Now, put things in perspective. Twitter generates about 80 petabytes of data every year. So you would need enormous amounts of disk space just to hold the state of the thing. And then if you're doing computation on it, then it's going to take a lot of effort.
Yeah.
Computational effort to do the stuff. It's not easy, it's not cheap. It gets hairy in a hurry, effectively, is really what it boils down to.
Yeah.
Yeah.
So what you mean is that this is the space you would need to basically store all of the data that it's producing?
Well, it's just so basically if I tell you here are 64 binary values.
Mm-hmm.
You would only need 64 bits in order to store the information. But if I give you 64 qubits, you would need 2 to the 64 complex numbers to store the state.
Okay.
And so effectively so when you want to deal with large numbers of qubits to do computation, so say, for example, you're only allowed to use 16 bits to do all of your computation, there's only so many computations you can do. Mm-hmm. You can't do more than 65,000 or so kind of computations with that, right? In the same way, if I give you only 12 qubits, then you can basically simulate it using 2 to the 12 complex numbers, but you can't really go very far with that.
Yeah.
But that's effectively, large numbers are why you want to do quantum computing.
Right.
Effectively. That's to put it very short.
Mm-hmm.
Well, actually, I'm about to ask you to expand on that, because my next question is, what are the benefits of quantum computing, and specifically, what kinds of problems does quantum computing help us solve with less effort?
So Look, popular science will tell you a whole bunch of stuff. Everyone's like really scared that quantum computing will break encryption and so on.
Right.
Um, the reality is a little bit more modest on that. So with a few, so think about a molecule. Okay, just think about a standard molecule.
Yeah.
Every electron in that molecule is interfering with other electrons in the molecule.
Yeah.
All right, and that interaction and interference has a profound, almost certainly defining impact on what the properties of the molecule are. So, for example, you learn very quickly in inorganic chemistry that if you have a transition metal somewhere inside the molecular structure, it's going to have a profound impact on what shape that structure is going to have.
Right.
And that has a profound impact on things like, is this going to become, a hexagonal crystal or a cubic crystal or whatever it is, and what color that molecule is going to actually be. Okay.
Mm-hmm.
Now you can do all of that without quantum mechanics, but effectively, where it all stems from is the electronic interaction between. Now, if you look at complex organic molecules that have metals in them, so hemoglobin, stuff in your blood, which is used, it performs a complex chemical reaction to bind to oxygen when you're when it's being forced through the lungs, and then it binds to carbon dioxide as it gives up the oxygen when it comes back from the muscles, right?
Mm-hmm.
Now that reaction is actually entirely a consequence of the electronic interactions between hemoglobin, molecular oxygen, and molecular carbon dioxide, with the various enzymes and stuff like that acting as catalysts in the body.
Right.
So one way of actually understanding how hemoglobin works is to actually look at the electronic structure of hemoglobin and start to get a sense of why it interacts that way with certain other things. And you can now start getting a better understanding of how these electronic configurations in hemoglobin will lead to this kind of interaction with oxygen, that kind of interaction with carbon dioxide, and indeed this kind of interaction with carbon monoxide, which effectively explains why people die when they breathe carbon monoxide, right?
Mm-hmm.
Now, to understand hemoglobin from a molecular level is something that we've kind of gotten a sense of just by looking at the bulk properties of hemoglobin of blood.
Sure.
But to look at it from an atomic and deeper level than that, you have to look at the electronic structures. Here's the kicker. Every time you bring a transition metal in, the big block of metals between the third column and all the way up to the point where you have 7 electrons in the outermost shell, 5. Those transition metals, they wreak havoc with calculations because the electrons just interfere all over the place. They have different types of orbitals. They're not easy to predict like hydrogen, which doesn't have any of the electrons in weird orbitals like P and F and stuff like that.
Yeah.
Right. So F and D, I should say. So to do simulation of transition metal chemistry using classical computation is extremely hard, and in fact becomes computationally infeasible very quickly, because you will need, for example, the most famous molecule that we work with is something called nitrogenase, which is found in the cell membrane of a nodule in the root of a bean plant, and actually allows a bacterium in that nodule to be able to fix atmospheric nitrogen to ammonia. This is a very, very profound, it's a reaction of very profound importance to human life, because it's the way we used to fertilize the ground without industrial fertilizer. And industrial fertilizer takes 3 to 4% of all the energy that we actually output as a human race every year in order to just make fertilizer to eat, so that we can grow food to eat, right? So this somehow the bacterium in this very constrained environment is able to take advantage of the electronic structure of nitrogenase in order to be able to catalyze a reaction that we cannot do easily. And we can't even understand how that works. And to simulate that, you need about 170 qubits. Now, to put things in perspective, 150 qubits would require 2 to the 150 complex numbers, and there are only 2 to the 150 atoms on this planet. Right? So for 170 qubits, you need 1 million planets like this one just to store the state. So you might say that it's actually computationally infeasible to go down the route of classical simulation. Right? But if we had 170 sort of electrons, then we could actually try and figure out how to make the thing work and get an understanding of how nitrogenase works. And that is effectively the first set of, in my opinion, the first set of really useful, profound quantum computations that will end up being seen. So we may not solve the nitrogenase problem, but we'll solve problems like that. There are very interesting chemicals all over the place. Chlorophyll is one. We don't actually understand from an electronic perspective how photosynthesis works. It'd be useful to do that, because if we could, then we could industrially make it work. And possibly reverse global warming. So there, any such molecule could have profound impact on the way in which we actually live. And you only need a couple of 100 qubits for that. It turns out to break encryption, you need twice the number of qubits as there are bits in the number that you're trying to break. So to break a 2048-bit number, you need roughly 4,000 something qubits. So well before we get to the point where we're dealing with thousands of qubits, we might actually solve some very profound problems before that. And I think that's what you want to be watching out for first. By the way, the whole quantum breaks cryptography thing is actually, it's theoretically true in that you can actually factor large numbers using an exponential speed up. It's one of the, in factoring numbers is one of those exponential speed up type algorithms. Okay. But post-quantum crypto is already a thing. It's already there, and you can replace your existing cryptography libraries with mathematically provable, secure ways of doing things that are even resistant to attack from a quantum computer. So it's certainly not the end of the world from the encryption point of view, and that's only telling half the story. If you say that quantum computers can be used to break RSA, for example, right? That's only half the story. You don't need to use RSA. There's much more strong algorithms that are already available.
Yeah, I would think you could always add something. Like in the World War II, there was a certain, when they were trying to break the code, that there's the variable of like which setting is it on, and I feel like even if you could calculate any solution that would be a cryptography, you could always add another barrier that would complicate it to a new degree, basically. Does that make sense?
It does. I mean, the term that you're looking for is to add entropy to the system.
Yeah.
And there are ways to add entropy to the system, and there are ways to actually add enough entropy to the system that even a quantum computer will not provide enough computational oomph to be able to do that.
So my next question is more your involvement of this with this at Microsoft. What is Q Sharp, and specifically, why do we need this new language to interface with quantum computing, and sort of what's the role of just sort of remapping old abstractions in familiar languages versus creating new abstractions?
Wow, that's a loaded question.
Okay.
It's a great question. So let me explain. See, if you're starting with the presumption that there are people in your audience that don't know what compilers are, then we should start there.
Okay.
Let me start there.
Sure.
Okay, so that's a brilliant question. Why we need a new language? What is Q Sharp? Why do we need a new language? Let's take a couple steps back here. Now, when you write a program and you run it against a classical computer, there are usually two techniques that you can do to actually make the program run on a classical machine. One is to use a tool called an interpreter, which basically takes one instruction at a time and performs that instruction on the machine.
Mm.
A second way of doing it is to take the whole program and run it through a tool. And what the tool does is it breaks down the program that you've got and tries to optimize the heck out of it so that you can actually get a big picture view of what the program's actually doing before it even starts running anything. So with an interpreter, for example, you could do a whole bunch of useless work if you write the program badly. You could compute values that are never used, for example. Whereas a compiler can actually detect that you're never going to use this value, so I never need to do this computation, and I don't need to generate code to actually run any of this computation. And now I can actually filter out and optimize things in a way that perform the same computation in the fastest and cheapest way possible. That tool is called a compiler. Now, with quantum hardware, it turns out that everything is precious. Time on the actual quantum device is precious. The number of quantum bits that you have is precious. So if you take a general purpose program that's there and you reuse library functions that somebody has written with no knowledge of what kind of hardware you're going to be running on, we can now take the program that you have written, fold in all of the pieces that came from the different libraries, analyze the program as a whole, and optimize the heck out of it so that we can now find the fastest and cheapest way to run that computation on the computer hardware that you've got. And notice now that you can write the program before you know what the hardware looks like.
Right.
So today you may have a chip that has 5 qubits from IBM. Tomorrow you may have one that has 72 qubits from Google. And day after tomorrow you may have something else that comes from Microsoft or some other manufacturer. And with each of these configurations, the kind of instructions that can be done optimally will change. So some types of operations will work better on one hardware versus another. And now you can actually but you don't need to know any of that when you write your quantum program. You write the quantum program at a high level without any knowledge of any of this stuff. And this compiler tool that sits in the middle can actually take a better understanding of what hardware you're going to run on and optimize for that hardware in a nice way. So to be able to sort of preserve the investment that you put into your program over time, it's better to use an agnostic way of actually expressing the program itself. And that's kind of why we picked a new language and a new compiling tool that can actually inject itself into this pipeline.
So you mentioned the IBM and Google have quantum computers built that, and IBM at least has it open to where you can actually start performing calculations on their quantum chip. Where is Microsoft? What's Microsoft's approach in this domain as far as hardware? Do you know?
Oh, absolutely. I don't know everything about it because all of it is like some of it's like pretty hair-raising physics, as in like they're on the bleeding edge of what physics looks like. But I can tell you this in terms of like for general consumption to get an intuition for what's going on. Turns out that not all qubits are created equal. So qubits, you remember I told you that these are quantum two-level systems?
Right.
Turns out that there's always going to be one state in the two-level system, one level in the two-level system that is more stable than the other state. So if you leave a qubit lying around, it will actually by itself over time degrade to the ground state. Okay, this process is called decoherence, and it's a force of nature. There's nothing you can do to stop it. I mean, one of those two states is inherently, fundamentally less stable than the other. Okay, now how long can you keep a qubit in a given state? That's a very good question to ask. And it turns out not for very long. Now, it turns out that in order for us to do anything useful with the qubit state the way it is, it needs to possibly be long enough to survive thousands of operations on it. And at the moment, the qubits that we have don't live that long. So there are two ways to go around solving that problem. One way is to actually have a lot more of these fast-dying qubits and somehow mesh them together in a way that they become one logical qubit as opposed to several physical qubits. And somehow get the logical qubit to live for a longer time. All right? Another way is to actually use the mathematics of how these qubits are formed in the first place and build qubits that take advantage of the physics that gives us this mathematical protection right from the get-go. And so IBM and Google and Rigetti and several other companies have qubits that are actually good physical qubits, but not very great logical qubits. They don't actually have enough to get a long-running computation going. But they certainly have ones that have the ability to demonstrate that they are behaving like qubits, like they're behaving like quantum two-level systems. They can do things like entanglement and superposition and so on and so forth. So they're great for demonstrating proofs of concept at the moment. But the state of the art is that nobody has a qubit that's going to be long-lived enough for you to do anything useful on. Now, Microsoft has put its bet behind something known as the Majorana fermion, which turns out to be a quasi-particle that we can construct that has this protection built in. So instead of having 1,000 physical qubits and then wiring them up to create a logical qubit like everybody else, we can actually generate a single qubit. At least we are hoping to work towards, when we're done, the single qubit will have the characteristics of those thousands of qubits that you put together to form a logical qubit. So we'll be further down the path of having a logical qubit when we actually have our Majorana qubit ready. And the Microsoft position on it is that we're expecting to get one by the end of this year.
All right.
So by the time we're done with this year, we should have a Majorana qubit, and now we'll have a qubit that is actually going to last longer than the competition because it's got the protection built into it rather than building the protection from having a whole bunch of discrete physical qubits.
Right.
So when you talk about the lifespan of a qubit, is this lifespan something that like gets reset, or is the qubit now have to be like replaced? Is this like, is it just you have to start over with it? Is it? I'm just trying to understand. Yeah.
Sure. So you're probably not old enough to remember cassette tapes, right?
we had cassette tapes when
we
I was
had
little.
some. Yeah.
Okay. So if you take a cassette tape and you move it through a magnetic field, the first time you move it through a magnetic field, it'll lose some of its information. So the sound just becomes a little muffled when you play it, right? If you do it a few times, then the sound becomes progressively more muffled until finally at the end of the day, you just get random white noise.
Right.
That's what happens to a qubit when you leave it lying around. So if a qubit will start off being perfectly aligned to either 0 or 1, or whatever it is that any state that you put it in, it'll keep that state. But then there is this natural cosmic sort of interference, or actually just any interaction with the environment is really interference. And over a period of time, the sound becomes fuzzier and fuzzier until you can't tell whether there was anything being said at the time or not.
Right.
And that the qubit will lose its value, it'll lose its state and become completely random. Right? So remember that you're dealing with probabilities before, right? So once you prepare your qubit in the appropriate state that you want to be in, then until you measure it, you expect it to hold on to that state. You don't want to set it up and then come back, 15 minutes later and measure it and find that it's decayed to some random position. That's not going to give you much value. In this particular case, you don't have to wait 15 minutes. It's about a millionth of a second. And it's already going to go it's going to go completely decoherent. And that's a millionth of a second isn't quite long enough to actually do anything significantly useful with the qubit. You can't actually perform more than 1 or 2 operations on the qubit at that time.
And is this a permanent change to the qubit?
Yes, you lose the information completely. It's in fact exactly like the cassette tape.
Okay.
You'll permanently lose the information that was on it. And in order to get the information back, you've got to re-record onto this sort of, the tape, the song that was there to begin with.
Okay.
Right?
That makes sense.
Yeah.
So it's probably very expensive to keep replacing these.
Well, it's not. It's actually more difficult than expensive in the sense that with the cassette tape model, for example, you could potentially make a copy of the song as soon as you got it onto another tape and sort of use those copies to synthesize the original song in the first place, right? And unfortunately, you can't do that with qubits because there's a whole bunch of mathematics around it that forbids you from arbitrarily copying state. So you can't say, here's 6 copies. I've kept now 6 copies of the same qubit. And now we can have 7 copies of the same qubit. And even if 3 of them die, I can now take a quorum and decide which one's going to win. You can't actually do that because you can't arbitrarily copy state between qubits. And so the mathematics involved in actually trying to do the error correction is a little more involved than just blind copying and zoring stuff out.
Okay. So it sounds to me like Microsoft's approach is sort of one more of meaning rather than expedience. It's focused on having a useful, robust qubit long term rather than having the newest, coolest thing that doesn't quite work as well as we'd like.
Well, look, we have, remember that the person who started, who was spearheaded the research on Microsoft's side was a mathematician who specialized in a branch of mathematics called topology. And if you think about, and here I'm going to really butcher everything up, but to really mush everything up, if you want to say that the ballness of a ball is its spherical state, right? Then any small deformation on the ball sort of destroys the ballness of it.
Right.
Mhm.
But if you said that the donutness of a donut is actually the hole in the middle and the ring around it, you could literally do quite a few things to that donut and still keep the hole in the middle. So, for example, you could take the donut and twist it, and the hole would still be there. It would still have this ring around it, right? And you've kept the donutness of the donut invariant under transformation.
Right.
So that branch of mathematics that talks about invariances under transformation is called topology, and we can use topological ideas to create these qubits where the qubitness of the qubit remains even under some amount of, interference with the environment.
I see.
So using using the mathematics of topology, we can actually sort of build a more resilient qubit, and that's the fundamental sort of driving point that started this whole game off in the first place. Don't ask me to extend the analogy too much because I've already butchered it quite heavily here.
That's all right. Are there any sort of topics within either your involvement in this or in quantum computing in general that you feel like we should hit in this conversation that we haven't hit yet?
Well, I think part of it might actually be like, what does a quantum computer look like, and how are we going to program it, kind of thing.
Oh, sure.
So this business of interfering with or interacting with the environment is a very fundamental problem. And one of the ways that all quantum computers have to deal with this is to actually effectively try to isolate the qubit and prevent it from interacting with the environment to the extent possible. And one way of doing that is to actually chill the thing to literally as cold as you can get. Physically, you can't go below absolute zero. So we go to like a few thousandths of a degree above absolute zero and chill the physical device so that the qubit that's maintaining the state is actually protected from interfering with the environment to the extent possible. So it's heavily insulated in many ways. A stray photon can't come and hit it, for example. You have to basically protect it against all kinds of stuff. So there's like a whole bunch of shielding, a whole bunch of chilling that basically makes this quite possibly the loneliest place in the universe, right? And that's really what you want to do, is you want to make it much, much colder than outer space and much, much more lonely than outer space. So, you want it to be so that stray photons don't get a chance to just come in and bash your qubit state out. So that magnetic field I was telling you about for the cassette, that is like stray radiation that's coming from, stray cosmic radiation is effectively that. Right. So you don't want that. So you try to protect the environment very heavily. And so, because you're running in a very cold temperature, you're running in this very isolated environment, it's not likely you're going to get one that you can keep in your front pocket and run with your phone, right? Or keep one on your desk or in your basement or anything like that. More likely than not, it's effectively going to be, some isolated environment that can be accessed via the cloud. And so Microsoft again has the sort of unique position where we want to build a quantum computer that is commercially viable, and you can basically monetize it by offering access over Azure. So we have the Azure reach, we have the Azure infrastructure, we have all of that stuff in place. And by the way, if it didn't if it wasn't clear to you earlier, what we're really talking about from the quantum computing perspective is to treat this quantum device effectively as a coprocessor for doing the hard math.
Yep.
And
Yep.
so it's effectively an external coprocessor that sits somewhere in the cloud, and you run your program in your traditional language like Python or C# or whatever it is that you want to do. And then when you hit the piece that says, okay, here's the difficult math that's going to take more than 1 million Earths to, say, maintain state of,
Right.
you then take that and you ship it off to the 200 qubit device somewhere in the cloud, and it performs the computation for you and then gives you back the result. You take the result and then you continue with it. And that's effectively the programming model from that point of view for how quantum computing actually works.
Yeah.
Right?
Yeah.
Alex, do you have any other questions?
No, I think that covers all the questions I had. It's interesting to see how little of the way that nature works that we're taking advantage of at the moment, and to just think about how much more potential there is out there to harness these qualities, even if we don't understand them. I find that to be really fascinating.
I think what you've said there is extremely profound. I mean, we have not even started to scratch the surface of what quantum computing is going to be. I mean, this is like you asking somebody, the day after the first transistor was made, about how we were going to get people to the moon, or how we were going to do Snapchat.
Yeah.
Right? Which arguably takes more computing power than getting somebody to the moon, right? But arguably, very arguably.
Yeah.
But the point is that the people who built the first transistor had only a mild inkling of what life was going to look like a mere 100 years later, or not even that, right? We're talking about stuff that happened in the 1930s and 1940s. It's not even 100 years since then. And now, you're walking around with a supercomputer in your pocket in the form of an iPhone, right? And you're playing video games that rival, that have augmented reality and all of that other stuff in there. Just the implications we haven't even reached the limit of what we can do with the classical thing. And now we're standing on the edge looking at what quantum computing can offer. And we're talking about the very first few things that you can kind of do. And we really have no idea what the next generation of algorithm designers are going to come up with, or how this is going to get exploited, either for good or bad, 20 years from now. We really don't know. So it's a very profound and humbling thing to be able to be at this point of human history where we're kind of like reaching out and touching, the heart of nature in a sense, where we can get a sense of how the universe actually works at that scale, and then try to sort of comprehend that and then exploit it to make life better. Right? So it's a very profound statement you made there, actually. And I'm glad you did, because I got the chance to sort of say a couple of words about my own thoughts on this matter.
I think that's an excellent way to close that topic. And so with that, we would like to transition to a segment we call the off topic. And John, I know we talked about this briefly, but the off topic can be anything you like. It can be a philosophical idea, a charity, something somebody said to you in line at the grocery store. If you can't think of anything, then I have an extra question for you. But
I think you should just ask the extra question, man.
Okay. All right. So here's the question. And this is outside of the world of quantum computing.
Sure.
What is the number one book that you recommend to people?
I actually give people the Bible.
Okay.
So I personally read the King James version. At least I used to for a very long time. I've switched over to the New International just recently, but usually I give people the Bible simply because, in some sense, it answers a lot of my questions, and in another sense, it's just the most beautiful use of the English language that you could possibly find. So just in terms of the turn of phrase, the ability for you to understand how human thought has evolved in terms of just the way you want to say something since the 1600s till now, I think that itself is very profound. So that's what I usually do.
Yeah, that's a great answer to the question. In my own experience, I think I didn't really have a good appreciation from a literary perspective of biblical stories until fairly recently. I started listening to this guy, Jordan Peterson. I'm not sure if you're familiar with him.
Yeah.
But he has a lecture series on YouTube about the psychological significance of biblical stories. And his plan from the start was it's a 12 lecture series, and each lecture he's going to go through one book after the other. 12 lectures in, he had just finished Genesis, which was incredible. But as somebody who did not have that appreciation before, that was profound for me.
Yes, and to be fair, right? Outside of the Gospels, the Genesis is actually is a very thought-provoking view on life, if you want to think of it that way, because the protagonists in there are almost never perfect.
Yeah.
And so the humanity of the people who have either a deeply positive or a deeply negative impact on the environment around them, it entirely relatable because I'm not perfect and I know it. And so every time I get the sense that somehow I feel like pointing my finger at somebody else, it's very humbling to look at it and say, hey, I could be that person. And so that actually has quite an impact on the way I think and the way I interact with people. So, yeah.
Yeah.
I think also just to better understand our culture, it's such a book that's influenced so many things that if you don't know the stories and you don't know how people have interpreted it and gained insight from it, you're missing a big part of our culture that a lot of people have. So as another way to connect with our history and people around us, I think it's very useful in that way as well.
Yeah, it goes back to the. I think there are many cultures that have been profoundly impacted by this the work that the both Western and non-Western, right? And so if you look at even India, where we landed up having one of the apostles actually show up there. So Christianity came to India very, very early on, first century, and so the impact is unquestionable, I think, from a cultural perspective. But I think it goes a little deeper, and from a personal perspective, the impact. I fully believe that if the impact isn't personal, it's actually of no value. And so from that point of view, I think that's something that I hold very dear to my heart.
Well, John, it's been a pleasure having you on the podcast. That was a great off topic. Thank you. And I really appreciate your input. If people are interested in following up with you or, understanding more about Microsoft and quantum computing, do you have any public presence that you want to pitch out there for us?
Sure. You should just go to Microsoft.com/quantum, and you should follow MSFT Quantum on Twitter. I'm available on Twitter as well, and a whole bunch of people that I can put you on to who are far more qualified than me to answer more difficult questions.
Sure.
Virtually everybody who works on the team here, from a quantum physics perspective, has at least one PhD. So they're going to be able to, you have access to a great number of people from there. So I'm John Azariah on Twitter, fairly easy to find. MSFT Quantum is the one you want to follow in terms of the actual announcements from Microsoft.
Yeah.
And like I said, Microsoft.com/quantum is where you want to go to download the quantum development kit and get started on stuff.
All right.
Great.
Awesome. Well, John, once again, it's been a pleasure talking to you. Thank you very much for coming on The Switch.
Thanks for having me over. Cheers.
Thanks, John.
Bye-bye.